Okay, I'm going to start section 10.4 now, which is polar equations in calculus. So similar to what we saw with parametric equations, how they kind of just talk about in general, what parametric equations are and graphing them and some things with the calculator and stuff like that in 10.1. And then they kind of turn to the calculus topics in 10.2. That like the same thing is happening here. So we'll talk about tangents and area and arc length. So we'll start off with tangents. It says to find a tangent line to a polar curve r equals f of theta, we regard theta as a parameter and write its parametric equations as x equals r cosine theta and y equals r sine theta. Okay, then using the method for finding slopes of parametric curves and the product rule, you have this guy here, dy dx. Now, you don't have to memorize this formula because there's a way to find it later. I'll show you at the bottom of this page here. But once you have this formula for dy dx, the derivative, you can make the following observations. The solutions to dy d theta equals 0, or when the numerator is 0, is going to provide horizontal tangents provided that the denominator is not 0. And then the solutions to the denominator being 0, dx d theta equals 0, are going to be where you have vertical tangents. So just like with parametric equations, provided that the numerator is not 0 also. And as a note, if both the top and the bottom are 0, no conclusion can be drawn about tangent lines. Okay? So let's take a look at problem 1 here. They want us to find the horizontal and vertical tangent line of r equals sine theta for when theta is ranging between 0 and pi. Okay, by the way, we can completely draw out this circle once on the interval 0 to pi, okay, which is like a lot of polar curves are going to be where you need the interval 0 to 2 pi, okay, not circles, okay. Let's see. Well, like just by looking at this picture here, I see that there's going to be 4 tangent lines. Okay, you got 2 horizontal tangents, one from the top of the circle, one from the bottom of the circle, and then there's a two vertical tangents, right? One on the left side, one on the right side. Okay, I just got to find those values where they're at, or the points. Well, okay, I need to find dy dx. So using this formula here. dr d theta, okay, so the derivative of r is cosine theta times sine theta plus r is sine theta times cosine theta. Okay, and I'm dividing that by dr d theta, that's cosine theta, times cosine theta, that's cosine squared theta. And then minus r is sine theta times another sine theta, that's sine squared theta. Okay? And so now let's go ahead and simplify this guy here. I got 2 sine theta cosine theta terms up top, and I'm dividing this by, let's switch over to the power formulas. And by the way, so make sure that you know the power formulas here. You're going to use those a lot in this section. Okay? So the one for cosine squared theta is 1/2 plus 1/2 cosine 2 theta, and minus sine squared theta, that's going to be 1/2 minus 1/2 cosine 2 theta. Okay, and this is the sheet there from section 7.2. So now, let's see, I'll leave the top as is. 1/2 minus 1/2, those are gone. And I got 1/2 cosine 2 theta minus a negative means plus 1/2 cosine 2 theta. That means I'm going to have cosine 2 theta down under. Okay? So, let's see. Where am I going to have horizontal and vertical tangents? Well, I'm going to have horizontal tangents when the top is equal to 0. So now, and again, I'm only on the interval 0 to pi. Okay, so pay attention to that. Okay, so if we set the top equal to 0 and solve this equation, divide both sides by 2, sine theta equals 0, when theta is 0, pi, 2 pi, but I don't want 2 pi, right? Because I'm on the interval 0 to pi. Zero, like, so again, I can completely trace out the circle one time on the interval 0 to pi, so I'm going to be back to my start point when I'm at pi. Okay, so that's why I didn't write pi there. When does cosine theta equal 0 on the interval 0 to pi? That's when theta is pi over 2. Okay, so the solutions to this equation on this interval would be 0 and pi over 2. Cosine of 2 theta equals 0 means that theta is, well, pi over 4, so cosine of 2 times pi over 4, that's cosine pi over 2, that's 0. Cosine of 2 times 3 pi over 4, that's the same as cosine of 3 pi over 2, that's 0 also. Now 3 pi over 4 is in this interval. Okay, so I must have that. Okay, and that's going to be all the solutions to these equations on the interval 0 to pi. So you're going to have two horizontal tangents. That makes sense, right? So like you can see that from the picture. And by the way, I'm going to give you pictures here on the quizzes and tests, and so check that. I'm not just drawing a picture just because it's cute. I mean, it's because it's a necessary thing that you'll need to look at, for your answers. You're going to have horizontal tangents at when theta is 0, r is sine of 0, 0. Okay, so at 0, 0, that's one horizontal tangent. That was good. And then with theta is pi over 2. Well, sine pi over 2 is 1. So at the point 1 pi over 2, here's the pi over 2 axis. If I go a unit up, that's another horizontal tangent. That was good. Okay. And then you're going to have vertical tangents at pi over 4 and 3 pi over 4. So sine of pi over 4 is 1 over root 2. Okay, so on the pi over 4 axis, I need to go out 1 over root 2 units, or about 0.707 units, to get to this spot. That's be where I'll have my first vertical tangent line. And then when theta is 3 pi over 4, okay, here's the 3 pi over 4 axis. And sine of 3 pi over 4 is also 1 over root 2, right? The opposite side is still positive. So I need to go out to about 0.707 units on the 3 pi over 4 axis. That'll put me right there. That looks good. Okay, so this information would be my answer to that problem. Okay, just as a note, instead of having to remember the formula for dy dx, this guy up here, you could employ the methods used to derive it. Okay, so like x is r cosine theta, right? I said that, and y is r sine theta. Okay, so r in this problem is sine theta. Okay, so x is sine theta cosine theta, y is sine theta times sine theta, or sine squared theta. So when I find dy dx, that's the same as dy d theta over dx d theta. The derivative of y with respect to theta, let's see, is me a chain rule. I'm going to have 2 times sine theta times cosine theta. Well, that's the same thing I got up here, right? And then dx d theta is going to be a product rule, right? So I got the first is sine theta times the derivative of the second, that's negative sine theta. So negative sine squared theta. Then plus the second is cosine theta times the derivative of the first is cosine theta. So plus cosine squared theta. Now, I've got cosine 2 theta there, right? But cosine 2 theta, that's the same thing as negative sine squared theta plus cosine squared theta, right? So using this double angle formula. So, if I wanted to, I could write a cosine 2 theta there underneath, and it'd be the same thing, I get the same values here. Okay. So maybe let's try problem 2 next. Okay. In problem 2, we have a cardioid given by the equation r equals 1 minus cosine theta. We're on the interval 0 to 2 pi. Okay, in part A, we want to find the slope of the tangent line when theta is pi over 2. So let's see, I got to get dy dx. Well, using this formula here, okay, so dr d theta is, I got, oops, let's see. So dr d theta is negative sine theta, so that's sine theta times sine theta is sine squared theta, plus r is 1 minus cosine theta times cosine theta. Okay? And then dx d theta, that's dr d theta, which is sine theta, times cosine theta. Okay? Then minus r is 1 minus cosine theta times sine theta. Okay, so that's where that formula is coming from. Okay, this guy here. So now the next thing is I'm just going to simplify this thing as far as possible. Well, let me distribute cosine theta into these two terms up top and sine theta into these two terms down under. Okay, that brings me to the next line. I got sine squared theta plus cosine theta minus cosine squared theta divided by, and then now down under, I'm going to have sine theta for all three of these terms, or excuse me, all two of these terms, I guess. And I'm factoring out a sine theta from those two terms right here. That's going to leave me with cosine theta plus cosine theta. That's 2 cosine theta minus 1. Okay? Now the next thing is up top, I'm going to switch everything over to cosine thetas. So sine theta plus sine squared theta plus cosine squared theta is 1. So sine squared theta is the same as 1 minus cosine squared theta. And everything else is going to stay as is there. So negative cosine squared theta minus cosine squared theta, that's minus 2 cosine squared theta. Now, up top, I've really got a quadratic. You know, I got a squared term, a linear term, and a constant. So this is going to factor for me, you know. When I factor this, I'll have 1 plus 2 cosine theta times 1 minus cosine theta. Okay, so when I FOIL that back, I should get the line right above up top. Now the next thing is, so I'm plugging in pi over 2, right? I want to find the slope of the tangent line when theta is pi over 2. By the way, I can already know that it's going to be some negative number, right? Because here's the pi over 2 axis. I could have known that before I even started. Okay, that I should be getting a negative number. Here's notation that you'll see in the book. So the derivative when theta is pi over 2 is how we'd read that. Well, if I plug in pi over 2, cosine pi over 2 is 0. So I got 1 times 1 is 1. Divided by sine pi over 2 is 1. Times 0 minus 1, that's negative 1. 1 divided by negative 1 is negative 1. So the slope of the graph here at pi over 2 is negative 1. Okay? Now, in part B of this, we want to find the points on the cardioid where the tangent line is horizontal or vertical. Okay, so I need to set the top equal to 0 and then the bottom equal to 0. When I set the top equal to 0 and solve this equation here, cosine theta equals 1 from this guy, and I'm on the interval of 0 to 2 pi, right? That's what they said. So theta, it would be 0, and theta is also 2 pi, but I would have completely drawn this out one time on that interval, so I'm not including that same start point there. And then when does cosine theta equal negative 1/2 from this equation? So, well, the adjacent side is -1. The hypotenuse is 2. It looks like 2 pi over 3 and 4 pi over 3. Okay. So over here, when I set the denominator equal to 0 and solve, I am, so I guess sine theta equals 0. That means that theta is 0, pi, 2 pi. Right, that brings me back to my start point there. And then when cosine theta equals 1/2, let's see, the adjacent side is 1, the hypotenuse is 2. On the interval 0 to 2 pi, theta is 3 pi over 2 and 5 pi over 2 when you flip that triangle upside down. Okay? So now theta equals 0 is in common to these two things here. Now when theta is 0, no conclusion can be drawn about tangent lines. Okay, and that makes sense, right? Because I got a sharp turn here. And you're not differentiable wherever you have a sharp turn. Okay, so that's something I could have known way back when I started this, that, you know, I'm not going to have any tangent line there at the origin. Okay? And it looks like from this picture, if I draw, you know, a couple of horizontal tangents, there should be, you know, 2 horizontal tangents, and it looks like I got 3 vertical tangents, just from this picture. Okay? And, well, I can now know the points where those happen. So you're going to have horizontal tangents when theta is 2 pi over 3 and 4 pi over 3. Okay, when I plug in 2 pi over 3, in that, cosine of 2 pi over 3 is -1/2. Okay, so I got 1 minus -1/2, that's 3/2. And, you know, so on the 2 pi over 3 axis, I need to go out 3/2 units, and that's me where that first horizontal tangent is going to be at. And then at 4 pi over 3, well, cosine of 4 pi over 3, that's -1/2. Okay, so 1 minus -1/2, that's 3/2. So on the 4 pi over 3 radial line, I also need to go out a unit and a half and plot a point, and that's me where my other horizontal tangent is going to be at. Okay. We're going to have 3 vertical tangents. So let's see, where does that happen? Well, when theta is pi over 3, cosine of pi over 3, that's 1/2. Okay, so 1 minus 1/2, that's 1/2. So at 1/2 pi over 3, well, here's the pi over 3 radial line. If I go out a half unit and plot a point, that's where my first vertical tangent is going to be at. That was good, right? And then when theta is 5 pi over 3, okay, cosine of 5 pi over 3 is also 1/2. Okay, so 1 minus 1/2 is 1/2. So on the 5 pi over 3 radial line, I need to go up a half unit there and plot a point. That's where my other vertical tangent is going to be at. Okay, and then also when theta is pi. Okay, so if theta is pi, cosine pi is -1. 1 minus -1 is 2. So on the pi axis, I go out 2 units and plot a point. That's where my other vertical tangent is going to be at. That was good. Okay, so in all, I got 3 vertical tangents and 2 horizontal tangents. And these are the points where those would happen at. Okay. We'll go ahead and stop the video right there, and I'll pick up with area then in the next video.